Welcome to the sixth and final session of Advanced Scientific Computing, Producing Better Code. This is a second session devoted to the issue of high performance computing. In the previous session, we focused mostly on using Julia well and knowing about some of the common performance traps that you can get into that are mostly focused on Julia's sort of ability to infer types. Now that you know how to solve those problems and you really can use Julia to its sort of full extent as a not slow language, we're going to talk a little bit today about the other things that you can do to improve the performance of the code that you write. So today's focus is really mostly on algorithms, which are really the other half of performance. And it's an incredibly crucial component of performance. A fast language, can be beat by a slow one if the slow one is using a smarter, better algorithm than the fast language is. So not just the implementation in terms of the language, but the implementation in terms of the actual solution strategy is really a crucial component of getting good performance. And this is a huge topic. It's one that's taught to every undergraduate computer science major. I'm assuming most of the people, watching this did not get that kind of training. And so this is really intended to be kind of an introduction to some of the key points that one would receive in such courses. One of the things that, in terms of its connection, though, to Julia, that I want to point out is that you can also get the opposite of the problem stated above, and that is that if you might come up with a wonderful algorithm, and really the best way from a theoretical standpoint that you could imagine solving a problem, and then have it run very badly if your language that you're doing your implementation in isn't an efficient computing language, isn't if it has overhead, and that's because the actual in practice performance you get from a language that doesn't do the optimizations that Julia does really depend upon what's been built in for you. So basically it relies on people having written the things that your particular implementation requires in a way that allows it to run quickly in that particular programming language. And invariably, you will find that certain constructs are efficient and other constructs are not efficient. And as I'll show you some concrete examples, that can change your impression of what the best way to solve a problem is. But that actually can be very misleading. And I'll show you an example of that. The advantage of learning about algorithms by using Julia is that because it can be compiled to efficient machine code, it really allows you to focus on the core aspects of algorithms themselves. So, in general, with Julia, if you choose the best algorithm to solve the job, you will get the best performance. That is not true of all other programming languages that are widely used in scientific computing. And so that makes Julia both good for the performance. Your code will run essentially as fast as you can possibly make it. And it's also good for learning, right? It becomes much more transparent, much more obvious why you're getting the performance that you're getting when your language doesn't impose barriers in its ability to implement the core computations that your reasoning about the nature of the algorithm suggests. And so I want to begin with a very simple example. And this is one that I've seen people who come from other programming languages solve in one way, and in fact, there's a much better way to solve the problem if you have an efficient language. And that is simply to say, if you have a list of items, what if you want to count the number of times that each value appears? So let me pick a particular example. I'm going to imagine, for just the purposes of illustration, that there are only 3 possible values that we might see, and we're going to generate a list of samples from among those choices. That list for this example is only going to be 10 items long. And we're going to be interested in what happens with many more choices and much longer lists also. But for purposes of illustration, this sort of shows you the kind of thing, and the problem that I'm wanting to address is a very simple problem, and that is to count how many 1s, how many 2s, and how many 3s there are that appear in this list. And this kind of thing happens all the time in practical code, right? This is these are, for instance, the results of a clustering algorithm or something, right? You may want to know how many points are in each cluster. If this is the cluster index that's been assigned to each point, then by counting the number that appear in each one, you figure out how many points have been assigned to each cluster. Many other examples in computing. Okay, so how might you go about solving this problem? Well, a common way, particularly for people who come from slower languages, might be to use a library function that allows you to count, and so Julia has such a function. It's called count, and we're going to implement that here. And in order to, we're going to do some benchmarking, and in order to benchmark this algorithm in its sort of purest sense, we're going to allow the answer to be pre-allocated. So what I'm imagining is that the answer to how many of each item they're going to be stored in this vector counts here. And it's my job as the person calling it to pre-allocate this. So if there are only 3 options, then this would be a vector of length 3, right? And the first entry would be the number of 1s, the second entry would be the number of 2s, and the third entry would be the number of 3s, right? And then the sequence that I want to analyze is the second argument here. And a natural way to try to solve this problem is to loop over every possible value you might get. So how many 1s are there, which is going to be the first question we're going to ask. And we're just simply going to count the number of items in sequence that are equal to 1, right? And so count in Julia lets you pass a function as the first argument. This creates a function that compares an arbitrary value to the value idx here, the index. And this will then return the number of items that are equal to idx, right? And then we store that in the counts vector. And then we go on to item number 2, and we ask how many items in sequence are equal to 2, right? And we store that, and we do 3, and then we're done, right? And we return the value here. Okay, so this might look like a good solution. And indeed, in some languages, this is probably the best way to solve the problem. So I want to introduce you, if you're not familiar with this topic already, to how you go about analyzing the expected performance of a particular algorithm. And so I want to introduce a couple of bits of mathematical notation. I'm just simply going to let m be the number of different options there are, how many different values might appear in the sequence, and then n be the length of the sequence, the number of observations that we're going to categorize according to the value that they have. Okay, and so if we go and we take a look at that implementation, we iterated once for each possible value of counts, essentially m times, right? And so what this predicts is that the total execution time of that algorithm should be approximately m times the amount of time that count takes to run, right? So, because we're calling count on each iteration, we're iterating m times, and so the product of those two things is going to be equal to the total amount of time. All right. Well, what about count itself? Can we estimate how fast count will run? Well, this is for a very lightly edited version of how Julia actually implements count. You pass in a predicate function, meaning it returns true or false for any value that you pass to it. We initialize the count by default at 0, and then for every element in the list, this would be our sequence vector. It's iter in the implementation of the method, where we go through and we call the function. And this, in our case, this would be this: is it equal to that idx variable? And we add 1, which is the integer correspondence to true. If predicate does return true, if predicate returns false, we add 0 to n. Okay, and so we just iterate through this entire list of things, checking each item and adding 1 each time predicate returns true. Okay, so this, of course, also is iterating, and this iteration is n times. And so since the total time that it takes to call count on that sequence is going to be proportional to n, the number of items in the sequence. And so the overall execution time of this implementation we would expect is proportional to the product of m times n. M because we call count m times, and n because each iteration of count costs n operations in order to run. So this is a so-called bilinear function, meaning it's linear in each of 2 variables, m and n. Okay? All right, and so just if we plug in some examples, not in terms of units of time, but just sort of total operation count, as it's sometimes called. If m and n are both 3, then you've got essentially a total of 9 operations you're going to perform. If m is 3 but n is 1,000, then there are going to be 3,000 operations. And if they're both 1,000, now you're talking about 1,000,000 operations or so. So you can see it grows rather rapidly as both of these grow. Now, is that the only way we could do this? And the answer is no, there is another way. And another way that we could do that is the following. It's the same signature. We pass in a pre-allocated counts vector and the sequence of items. But in this implementation, what we do is we first set each element in counts to 0. So we're initializing our counter here. And then we're iterating through the sequence. And in this case, I've set up the problem so that the value in sequence is the index that we would like to increment in counts, right? So all we have to do is say, I just want to add 1. So this will tell you which place to store the increment. And we just increment that slot in counts by 1. And when we finish this iteration, we're completely done with the problem. So we never had to call count in this implementation because we're counting them as we in all of the different possible values as we encounter them as we iterate through the sequence. Okay, so how fast might this execute? Well, there are kind of 2 obvious steps. One is we have to initialize all of counts to 0. And then we have to iterate through all of the items in sequence. And so the total time is going to be proportional to the sum, since there's 2 sequential steps, of the amount of time that this fill operation takes to execute, plus the n, since that's the length of sequence, times the amount of time it takes to increment counts. Now that is just a single operation. So we can sort of think of that as something that is effectively like 1, basically, right? It doesn't depend upon any of the parameters m and n that we're discussing. And now what about fill? Well, fill sets each element of counts to 0, and so that is iterating through the elements of counts and setting each one in turn to 0, and so that time must be proportional to m. And so the net effect is that the total time is now proportional not to the product of m and n, but it's the sum of m and n. And that is linear in each variable separately. And if we fill out this table, we add essentially a new column to it. Now you can see that the effect of this change in the way we decided to implement this function is dramatic, right? In the first case, you know, they're both fairly small when m and n are both small, but by the time we set them both to 1,000, there's 1,000,000 operations to do it via count, and there's only 2,000 operations if we do it the second way using indexing, right? And that's a massive, massive savings in the sheer amount of work that needs to be done to implement what is otherwise the exact same final result, right? And so, you know, the difference between a poor choice of algorithm and a good choice of algorithm can literally be orders of magnitude. And just to sort of show you how this works out in practice, before I started this lecture, I ran some benchmarks, you know, each combination of m and n many different times to get accurate timing measurements. And I saved them to a file and loaded them before this session here. And I just want to plot the results for you and show you what you get. This is a 3D plot, and I'll walk you through the axes. Let's first start with this axis here. So the horizontal axis is the number of samples. So this would be n, the number of different observations in the vector that we're counting the individual observations from. And this is plotted on a logarithmic axis, base 10. So essentially this means that there were 1,000 entries in that vector. This means there were 10,000 entries, 100,000 entries, and 1,000,000 entries. And you can see that both algorithms, shown here in green and purple, 2 of the Julia logo colors, you can see that they both show the expected linear increase with the number of samples, right? So just as our formulas were suggesting. Oh, and I should have said that this vertical axis is the amount of time it took, also on a logarithmic axis. So if you plot a linear function on either a linear or a log axis, it looks linear. Let's look at the other axis of this plot. This one is the number of choices. This is essentially the m component. And again, as predicted from our analysis of these algorithms, you can see that the one that's bilinear shows a linear increase in the number or in the time with the number of different choices, whereas the linear algorithm looks essentially flat, and that's basically because over this parameter range, the execution time is really dominated by the larger of the two values, and that is the number of samples, basically. Another thing that's worth pointing out is that essentially for all parameters, the linear algorithm beats the bilinear algorithm, but simply because the log of the running time is, even for the very largest samples, on the scale of a millisecond or so for the linear algorithm, and on the scale of a second or so for the bilinear algorithm. So you can see that's 3 orders of magnitude effectively. It's an enormous difference in terms of efficiency. You may have noticed, sharp-eyed viewers may have noticed, there's actually a case where I dip slightly below. That's really for the case where there is I think, what is it, just one sample, and that essentially ends up having to do with bounds checking in the arrays. Our implementation does need to check bounds to make sure that the vector doesn't include items that are bigger than the counts vector that we supplied. But aside from that kind of trivial circumstance, in essentially every other parameter regime, our linear implementation is the one we would unquestionably like to go with. So what's very satisfying about this is that we can see that what we got out of this really matches our expectations from the analysis of the algorithm, and the runtimes really are quite good. I did the same thing. I translated this code also into Python as a way of comparing the performance there, and likewise measured all of the run times before this session started. Let me show you now on the same plot what the two-language comparison looks like. So again, if you look along the samples axis, you can see all four implementations increase linearly as expected. And if you look along the choices axis, you can see that the run times are essentially flat in the linear cases because they're dominated by the number of samples, whereas they're linear for the two that are based on calling counts. There are, however, 2 features worth noting. The 2 Python implementations, which are colored according to colors in their logo, you can see in all cases are slower than either of the Julia implementations. But perhaps that's not surprising because we know that Julia is a faster language than Python. And again, the differences here are sometimes vast, right? Orders of magnitude. The thing that's maybe a little bit more surprising is that while in the Julia implementation, it's worked out as expected, that the linear algorithm consistently beats the bilinear algorithm, in Python, we see it's the converse, right? That the linear algorithm, which is the better algorithm, right, is consistently beat by the bilinear implementation. And that has to do with the fact that the overall performance of the code is really dominated by limitations of Python. In particular, count is implemented in NumPy, and that therefore is fast because NumPy is written in C. Whereas when we wrote our linear implementation, and when I translated it from Julia to Python, it's just using a for loop, and Python is slow at running for loops. And so you can see, in fact, the better algorithm is the one you don't want to use in Python when you implement it this way, because it actually runs vastly slower, except for all but maybe the absolute largest data sets, basically. And so the consequence of all this, is that you can get some misleading impressions about what makes a good implementation and what makes a bad implementation if your language has limitations. So just to sort of hit something that, I mean, you basically already told you this, but this ability to just sort of estimate in a kind of a back of the envelope sort of sense the performance of code is a really important thing to develop and become almost sort of like a reflex when you look at code whose performance you care about, right? And the simplest trick of all is simply to track the loops, and especially since you use loops a lot more, or can use loops in Julia code, that's in some ways very easy to do, right? So if I had a loop nest like this, right, this actually corresponds to 2 loops. The inner loop is the J loop, and it iterates n times, and then I iterate that inner loop m times, the I loop, right? And I do something. And so just by looking at this, you know that this code is going to have a running time that is at least proportional to m times n, right? Now, it's going to, of course, also depend on how expensive this inner operation is, and there may be important additional things that you would then, sort of put into this as well. But without even knowing anything else about this code, your prediction is that it's going to have at least a factor of m times n in front of the runtime of this code. So you can use these very, very simple types of analyses to make estimates of all kinds of real world code. I want to cover another example, and this is actually this is a warm up to fulfilling a promise I made during my last lecture when we were using profiling to discover bottlenecks in our code. And there we discovered that a matrix multiplication was really the dominant component of one of our calculations, and we discovered a better way to implement it. And now what I'm going to do is walk you through the reasoning by which you could figure that out on your own. Profiling directed our attention to the matrix multiplication. Now we're going to understand why that was slow and why the alternative design is a better one. So we're going to warm up to that first by looking at matrix vector multiplication. And you may know that when you multiply a matrix times a vector, you get a vector out. And that for each entry of the output, what it corresponds to is that corresponding row of the matrix, take the dot product with the vector, meaning each entry of this gets multiplied by its corresponding item, and then all those get added up into the final result there. And so if there are n columns to this matrix, equivalently n rows to this vector, then you know that every step of that process is going to be a loop of length n, right? And so the overall implementation of matrix vector multiplication might look something like this. And I'll just say at the outset that this is a fairly naive implementation, but for our purposes, that's all we need. So we have two loops here. The inner loop is iterating n times, and the outer loop is iterating m times. And so really, without knowing much of anything else, you know that the total time here is going to be proportional to m times n, okay? So this, I want to sort of introduce a notation that's frequently used both in documentation for software and in any discussion of algorithms, and it's called Big O notation. And the point of Big O notation specifically is that it's essentially freedom to ignore terms that are less important. So in that analysis that we just did of that code, you might object. You might say, hey, you're ignoring certain things. You talked about this inner loop and the number of times it runs, and then how many times the outer loop runs, but you didn't pay attention to the fact that there's a little bit of work ahead of time and a little bit of work after time. And that is true. It's absolutely right. So this line runs m times, and this line runs m times. And so if you really wanted to do your bookkeeping carefully, you might say that the actual running time is some coefficient, some number that essentially corresponds to the time of each iteration of this line plus the time of this line, times m plus another coefficient, which is essentially the amount of time this line here takes, times m times n, since that line runs m times n times over the course of executing this set of nested loops, right? So this would be, certainly it is a more accurate description of what the runtime of this overall loop is. The point of Big O notation, though, is to pay attention to the things that grow most quickly. And so you only keep the leading terms. For anything other than tiny values of n, m times n is going to be bigger than m, presuming that these coefficients are not radically different from one another. And so Big O notation is essentially a way of granting yourself license to ignore the small stuff and just focus on the stuff that dominates the overall runtime. And so in Big O notation, we might say that this algorithm here is of order m times n, Big O of m times n. And you'll see that kind of notation all over the place. It's worth emphasizing that when you use this, there's actually, when there are multiple variables, there isn't an entirely uniform standard for how you do this, but my recommendation is that you keep all the terms that might potentially be the leading order terms. So for example, If you do an analysis of an algorithm and you discover that there's one term that's proportional to n squared and another that's proportional to n cubed, well, when n is big, this term is going, all else being equal in terms of a and b, this term is going to be vastly bigger than this term, right? And so it's fair to say that this is an order n cubed algorithm. But if you do an analysis of a different algorithm and you come to the conclusion that there's one term that's proportional to n squared, another that's proportional to the product of m times n, and then two linear terms, well, the linear terms are going to get beat by these terms here, right? But which of these is the most important one is going to depend upon the specific values of m. If m is much bigger than n, this one will dominate likely. And if n is much bigger than m, so the converse, then this term will likely dominate. And so the safe thing to do is just say that this is an order n squared plus mn algorithm. And here you're kind of dropping any of the coefficients in your description of how this behaves. So armed with that, with the big O notation and understanding of how to analyze these algorithms, now let's actually turn to that example from our last session, right? So in this case, our first implementation of this, so we wanted to implement an algorithm that computes A times B times X, right? Where A is a matrix, B is a matrix, and X is a vector. And so the first time we implemented it, we first calculated the matrix A times B. So we started multiplying from the left of the expression and worked our way to the right. And then after we computed that product of those two matrices, we then computed the matrix vector product and returned it, okay? And we discovered through profiling that this was the most expensive line. And we thought about it for a little bit and realized maybe we could group the expressions differently. And so in this implementation here, we first multiplied we grouped the last two terms together first, and we computed the vector that results from the second matrix times X, and then we multiply by the first matrix. And up to your round off error, these two give the same answer, right? And so now, okay, so, and we got a huge win in terms of our performance from grouping our computation this way. Now let's actually see why. And just for simplicity, we're going to use square matrices here. So I'm going to imagine that m is equal to n. And you may know that the rule for multiplying matrices is kind of the same as it is for vectors. It's for every entry in the output, you multiply a row, you take the dot product between a row of the first matrix and a column of the second one. It's just that when you're dealing with two matrices, there are multiple columns of the second element here, but yet each one of those corresponds to a single entry here. So each one of these takes order n to compute, but in the output, there are n squared such entries. And so the total execution time for matrix-matrix multiplication is of order n cubed. And so if we do our analysis then of this bit of code here, we can see that the matrix-matrix multiplication is order n cubed, matrix vector multiplication is order n squared, and that's to be contrasted with the second implementation in which both steps are order n squared. And since order n squared is better than order n cubed, often vastly so if n is large, the second implementation wins hands down. And indeed, that was consistent with the results that we got from benchmarking and profiling this code. Okay, so that gives you a sort of a practical sense of how you go about leveraging this understanding of how to estimate the running time of algorithms in design and choosing one that's good for your particular use case. I want to give you one final example that shows a different scaling behavior than anything we've seen so far. And this is called binary search, and it's a prototype of many different kinds of algorithms that are used in throughout computer science. And sort of a game that is a good prototype of this is just, if I'm guessing a number between 1 and 100, guess which one it is. Well, how efficiently you can solve that problem depends upon how much of a hint I'm willing to give you. If I'm only willing to tell you you're right or you're wrong, you might actually have to guess all 100 numbers before you get it right? So there's no, and it doesn't matter what pattern necessarily you guess in, because there's nothing about guesses that's informative other than the fact that you're not done yet. You still have some to explore, right? However, if I'm willing to tell you more, and that is each time you make a guess, I tell you whether the true number is bigger or smaller than the number you've just guessed, then it turns out you can answer this question in 7 tries. And this is probably quite familiar, I imagine, to many people watching this. But in case it isn't, let me just show you how you go about doing that. So your best strategy is to split the overall range of potential values in half. And so you might start by guessing 50. And if I tell you that it's smaller, then you know at the outset that the values can only be between 1 and 49. You know, it's not 50 because I said smaller. Now I guess 25, and or you guess 25, and if I say bigger, this should actually be 26 to 49. You know, and so you've narrowed the range further. And note that both times here we've essentially cut out half of the remaining entries from the realm of possibility. So instead of essentially discarding a single value on our first guess, we've actually discarded half of the values on our first guess. And so we continue that process and we narrow in. Here we happen to hit the right answer on the 6th iteration. Had I picked 31, it would have, and this had been the pattern of guessing, it would have taken 7 trials, but there's no way if you use this strategy for it to take any more than 7 trials. And so since we're cutting in half on each iteration, then the number of times you have to do this is essentially to the point where 2 to the k is bigger than or equal to 100, which was the number of original values. And since that's satisfied for 7, that's why it takes you no more than 7 guesses to get this. And so that relationship, when 2 to the power to the number is bigger than however many entries in your list, is logarithmic scaling, right? You can solve for k by taking a logarithm of both sides. And so you would say that solving this problem is an order log n problem, right? Because it's it increases with the logarithm of the number of entries that I allow as choices for this problem. Turns out that many algorithms in computing have efficient log n or order n log n solutions to them. And so this, you'll see logarithmic scaling in many descriptions of key algorithms that are widely used across the field. And in general, most of these arise in situations like this, where it's a so-called divide and conquer strategy, where you can really winnow away the range of possibilities by a multiplicative factor on each iteration of the algorithm. Okay, so that's all I want to say about algorithms. And again, if you were undergraduate in computer science, you'd have an entire semester devoted to algorithms, and you'd study many algorithms in much greater detail than I have today. But what I was hoping to do basically is give you enough of a taste of this subject that you can actually start using it even without that sort of detailed and deep study. And it's very worth it to know much more that I've said, but this at least gives you the ability to start thinking in these terms. I want to turn to another topic that's actually quite important for performance, and it's also one that many people think of when they think of performance, and that has to do with one aspect that is different from anything we've really discussed so far in the course. You may remember from my very first session that I differentiated not slow languages from fast languages. And I want to now get much more specific about what I mean by that distinction. So Julia, as I've argued, is wonderful for studying algorithms and learning how to use algorithms effectively, because it lets you compare them almost in a pure sense, meaning it's almost a match to the sort of mathematical properties that you would write down about the behavior of that algorithm. The language doesn't add unnecessary overhead to the operation, so it really lets you see the sort of core nature of the algorithm. And that's almost true, but it's not true in every circumstance. And the difference is that while, Julia, the language doesn't impose barriers that are kind of artificial or idiosyncratic about a particular implementation, computer hardware does, right? And since Julia runs on computer hardware, there's really nothing that Julia can do about that. And so knowing something about the idiosyncrasies of computer hardware and optimizing your implementation, not just in terms of, say, operation count, but also in a manner that's aware of these idiosyncrasies and limitations of computer hardware, and designing your your algorithm to take account of those, work around the limitations, and take advantages of opportunities. That's the distinction to me between between code that is simply not slow and code that is truly fast, meaning you've really thought very deeply about this fact that this is running on modern computing hardware and figured out a really good way to implement this. And so this requires, of course, a whole different set of expertise in some ways. I'm only going to scratch the surface of this, but I want to illustrate just a couple of the principles that are important for making that transition from writing code that isn't slow to code that is writing code that is genuinely fast, right? And again, I'm just going to scratch the surface here. There's a great deal of information about this out there, and I strongly encourage you to consult these other sources for it. But one very important example of these kinds of idiosyncrasies have to do with memory and something called the cache. So it turns out that accessing memory on your computer is actually quite slow. It's much slower and generally to access data stored somewhere in your computer than it is to compute. Often it's cheaper to recompute something than it is to look it up in some place where you stored it. Now, this is not inevitable. It is actually possible to build extremely fast memory. It's just that it's also extremely expensive to do so. The cost of a computer that has nothing but fast memory would be so prohibitive that no one would ever buy it, right? And so what the designers of machines have done is that they have actually provided you with multiple types of memory that have different trade-offs. So the main memory of the computer has the ability to store vast quantities of information, right? And this is really where most everything on your computer is stored temporarily, obviously permanently on the hard drive, but transiently in the memory of the machine. However, if this were the only thing you had, it would drag the overall performance of the computer down drastically. And so what the architecture designers have done is they've enabled capabilities to transfer actively used memory from the main memory to a much smaller region of memory that's often called the CPU cache. And this essentially might contain a copy of the information that's available in memory, but accessing this very expensive but very fast memory. And the CPU can make use of it to actually implement very fast computations. Now, this is the sort of most trivial illustration of what this looks like. In reality, there are several different kinds of cache, the so-called L1, L2, L3 cache. Some of you may have seen on specs of CPUs. But those are essentially just variants on this, where the different levels of cache have different trade-offs between cost and performance and capacity. For those of you who get interested in this, there's an absolutely phenomenal resource, the so-called What Every Programmer Should Know About Memory. It's a large and fairly complicated document. I'm not actually convinced that every programmer needs to know everything that's in this document, but it's an extraordinary resource and highly recommended for anybody who really starts getting seriously into this topic. And it's where I drew this figure from. The sort of very brief sort of statement that is a much more minimal expression of what people should know about memory can be reduced almost to a short list, right? And that is, so I mentioned that the computers can have multiple layers of this cache, copies essentially of the main memory, that are smaller but faster. The very fastest of these caches often have only about 1/1,000,000th of the storage of your overall main memory. So they are tiny compared to the amount of data that you can actually store in memory in the computer. It's worth knowing that main memory does not get transferred byte by byte into this cache. Instead, it actually gets transferred in small chunks. And these are pretty small, often like 64 bytes at a time, right? So that's equivalent to 8 float 64 numbers in a row, in a vector, for example. But the key part is that it's adjacent blocks of values that get transferred into that. That's called a cache line. And so, and you can't address the memory. You can't get it into cache by copying anything less than an entire cache line. And because the cache is very efficient and the transfer process is quite slow, the key thing to keep in mind is that your performance is always going to be better if you can get every ounce of value out of what you currently have in cache before discarding it and moving new chunks of memory into it, right? So you don't want to do a tiny bit of work on what's in cache, flush it, bring in new memory, do another tiny bit of work, and then have to go back to the same bits of memory later on. That would be a poor design for your overall algorithm. The final thing that's worth knowing is that CPUs are quite smart, and they actually try to predict in advance what chunk's going to be needed next, and they'll start fetching it in many cases before you actually start using the memory. So before you get to the line in your code that needs access to it, they've already looked ahead, to the future to try to predict what you're going to need and hope to have it waiting for you by the time your code gets there, right? And so the consequence of this final thing is that if you have predictable patterns of access of memory in your code, it will be more efficient than unpredictable patterns of access. Okay, so this is very brief. This is far from sufficient to turn you into an expert in this. You'd really have to spend much more time studying the details of this. One of the good things, again, about Julia when it comes to this kind of optimization is that there are many cases where you don't really have to worry about this yourself. And there's an absolutely wonderful package on Julia called loop vectorization. And its basically a whole purpose in life is to understand these details of how hardware actually works, right? And what loop vectorization does is it tries several different implementations of the core computations of your code, and it will estimate in much the same way we have during this lecture what the actual runtime of each implementation will be, and then it will simply select the best of them. And so loop vectorization is phenomenal for helping make changes in how, so you can write your code in a quite naive way, and loop vectorization will reorder your loops and do other kinds of transformations to your code that can really help code that isn't slow become truly fast, right? And so that's a very nice resource. So it's worth knowing about this kind of thing, but at least in practice, in some circumstances, you don't have to deal with the complexities yourself. The final topic that I want to get to is the topic of parallelism. And this is often actually what people think of by default when they think of high performance computing. I really think of this in a much broader sense than just parallelism, but it's unquestionably a very important topic when you discuss high performance computing. So one of the reasons this has become so important is because CPUs have, by and large, they've certainly slowed down in their rate of speed increase. They're nearly halted in their actual overall performance. And so the way that the CPU designers have responded to this is, instead of trying to make them always faster and faster, by and large, what they're doing is they're just giving you more and more of them. And so in order to harness that power, what you might like to do is to take a task that would, in sort of the simplest code you might write, execute serially, meaning all in order, and you just start at the beginning and you go all the way to the end, and instead break it up into chunks and assign different chunks to different actual CPUs, different computational units, different cores as they're called, in your computer, and have each core work on a portion of the computation, and then get the final results that way. And so this is a model here called multi-threading. There are other variants of the same thing that include GPU computing and distributed computing that are essentially analogous to this, but just with different architecture. So this is the idea behind parallel computing, and it has many advantages when it is applicable. And it's kind of the go-to that people who use slow languages use, because they don't have many other options for speeding up their code other than calling code that's written in a fast language and or parallelizing. Now, so again, in Julia, sometimes you don't need this extra step because your serial code is so much faster, but there are many problems out there which are not practical to solve, even on a laptop. And so in which case you need a little more serious use of compute resources, and this parallelism becomes a really vital tool. And so Julia does make it quite easy to use parallelism. You can launch Julia with multiple threads here is an example of launching Julius that has 4 computational threads. And I started this notebook in that mode. So if I ask the threads library, how many threads is this session currently running with? It will tell me there are 4 threads. And so if you see that kind of output, then you can use parallelism. If it says 1, then there's no point in trying to structure your code with the threads library, as I'm about to tell you, or often no point anyway. It depends. There are circumstances where it would still make sense, but in the simplest cases, there'd be no particular reason to use threading if you only have one thread. So so what I want to show here now is this is essentially taken straight out of Julia's manual, what you might be able to do with threads. So what I'm going to do is I'm going to write a loop. And in each iteration of the loop, I'm going to call a function called thread ID. And what this does is this returns the thread number associated with whatever thread is handling that call. And so I'm going to iterate. I'm going to create storage for 8 different values and then iterate 8 times. And each time I'm going to store in this vector which thread was handling it for that particular entry in that vector. And so if we do that and we take a look at the results, you can see that the first 2 entries get set by thread 1, but the second 2 entries get set by thread 2, etc. So each of the 4 threads takes 1/4 of the work. And in favorable circumstances, what this might mean is that we could literally finish this computation 4 times faster than we had before. And that's obviously fantastic when you can pull that off. So there are, though, some caveats that you should be aware of. So first of all, Julia's threading library is quite efficient, but nevertheless, anything that you wrap in an at threads has an overhead of a few microseconds. And this is equivalent to several thousand additions and multiplications, for example, right? And so you would not want to use this for fairly trivial computations. You should reserve the use of parallelism in general, even multi-threading, which is one of the fastest forms of it, for sizable jobs where there's a lot of computation that needs to be done, and an overhead of a few microseconds is going to be washed out by the overall running time of the code. And so with that bit of understanding, in cases where you can arrange it so that the threads can all work independently of one another, it really is possible to sometimes get about an n-fold speed up if you're using n threads, and that's fantastic when that can happen. However, there are gotchas there too, and that is that the communication between threads can be a source of bugs or slowdowns. And I'm going to illustrate the bugs part of this more directly than slowdowns, but naive attempts to resolve these bugs can give you very large slowdowns. And these slowdowns are not trivial. Sometimes the threaded implementation, the steps you need to avoid bugs can sometimes make it slow it down so much that it's slower than the single threaded naive implementation of the algorithm. So again, you need to be aware of the caveats of this if you're thinking about reaching for parallelism. So let me illustrate how the bugs arise first. So what I'm going to do is I'm going to write here, this is a function that I've written that computes the sum of values in a vector v, right? So I'm imagining they're all integers. I'm initializing my sum to 0. And then I have my threaded loop, right? And I'm just so that, if I got rid of this might look exactly like how you would write a summing operation if you're adding up a bunch of integers. But I'm putting this threads at threads around it, and that's going to then distribute the work across the multiple threads. Sounds phenomenal, right? Really nice thing to be able to do. And so let me initialize a vector here. So I'm going to draw random numbers between 1 and 5, and I'm going to draw 10,000 of them. And then I'm going to call this function on it. And when the value comes back, you might be immediately disquieted, because remember, none of these were less than 1. And we drew 10,000 of them, but yet the total sum is smaller than 10,000. That would mean the average value in this list appears to be less than 1. Now, this can't possibly be correct, right? And we can see that for sure if we just do ordinary sum. You can see that indeed we've got something in the ballpark of 30,000 here, which is a much more reasonable number. So what is it that happened? Why did this go so wrong? Well, if you look at this code, if you think through the execution, what you can see is there's a couple of steps. So first of all, essentially you have to read out the old value of S, and then you increment it by the next item in the list, and then you store that result back in S again. One of the things that can happen with code like this is a so-called race condition. So if you have multiple threads working, so let's say we've got the 4, and let's say things are particularly unfortunate. 3 of them are working pretty fast, and one of the threads, right after reading out the value of S, gets interrupted. Maybe your computer decides it's time to check to see if you've received some new email or something like this, and for whatever reason, it picks that core that this thread was running on to go do something else for a little while. And then after it's finished that job, it comes back and it picks up execution where it left off. Well, the problem is you've read out what's now a very old value of S. It's been incremented many times since then, but you read it out and you don't know that it's been refreshed. So you add your number to it and then you overwrite the value that you had before. And so this causes it to essentially drop many of the terms from V, and that's why this surely represents a sum of a subset of the values in V, but it's an uncontrolled and unreproducible subset. And it all just comes down to the very specific ordering of operations that occurred across your 4 simultaneously executing threads. And so these are called races because it does depend upon exactly where each thread is in its execution. And so these bugs can arise when values from one thread overwrite the partial work of another thread and essentially end up discarding some key work. So the good news is this is a very readily solvable problem. One way you can solve this is you can essentially prevent one thread from accessing S while another thread is busy using it. And there are cases where that's the best solution to a problem. Those are called locks or mutexes or atomic operations that ensure that things happen as a distinct unit without the potential for anything else happening in that time. And these are very useful constructs to know about in contexts where you need them. In this particular case, there's a much more straightforward solution that also doesn't introduce any slowdowns. The problem with locking and its generalizations are that while one thread is holding the lock, others simply have to wait until the first one is done with it. And so that delays the threads. And in unfavorable circumstances, it can take way, way longer than just a single threaded implementation. But in this case, what we can do is we can ensure that each thread operates independently by allowing each thread to maintain its own counter. And so that's what this implementation does here. This one here allocates a number of counters equal to the number of threads, and then each counter increments just its own particular, each thread increments just its own counter. And at the end, so for 4 threads, this would just simply be a list of 4 values. And then at the end of running the threads here, then this would return the sum of the 4 values that were accumulated by each thread. And so if we run this, now we can see, that it gives a plausible value. And in case you forget, that actually is exactly equal to the single threaded result that gets returned, which hopefully is correct. So in this case, all we had to do was give each thread its sort of own private counter to increment, and that resolved all the race conditions that our first implementation of this code had. So very often in parallel computing, solutions like this are readily available. And so under many circumstances, you can resolve these kinds of problems easily. Certain algorithms don't parallelize quite as neatly because they rely on decisions made on the basis of previous computations. And under those circumstances, it requires much more finesse to design a good parallel algorithm. So The threading is the easiest form of parallelism in some ways, and it's very, very high performance, and it's widely available because basically almost every CPU these days has multiple cores in it. And so, it's what I recommend sort of for some of your first experiments with parallelism. Julia provides many other opportunities for parallelism, and two of the biggest ones are GPU computing. So there's a whole GitHub organization called Julia GPU that has multiple packages. Some of these packages let you essentially define arrays on the GPU and then manipulate them as if they're the same as arrays you would manipulate using high-level code in core Julia. And that makes life very easy. One of the Julia's distinctive advantages in the GPU space is that Julia code can be compiled down to the code that runs natively on GPU. So you can write so-called kernels even in Julia, for very custom operations that you want to customize very heavily. So Julia is fantastic place to do GPU computing. It also supports a form of computing called distributed computing, and this is basically when you divide a task across multiple physical computers, right? So you may have a whole room full of servers, and each server is working on a portion of the same problem. And so this so-called cluster computing is supported in part by Julia's distributed standard library and other packages in the ecosystem. So, all of these things are great, and there are many, many problems where they're really a necessity if you want to be able to tackle very, very large computations. But again, I do want to caution you that if you're coming from a slow language, you may essentially reach for parallelism almost reflexively, right? And I want to urge you not to do that with Julia. Really, your first step, you'll get the most benefit from this if you spend some time first optimizing your code to run in straightforward single-threaded mode. You'll, first of all, iron out any performance gotchas that you have in your code that might waste a whole bunch of computation time, regardless of whether you parallelize it. And then if you have done all that and you've really taken a serious look at your code, you've chosen a good algorithm, you've implemented it well using idiomatic Julia, then and if it's still not fast enough, then that's the time to reach for parallelism. And it's a very well justified choice in that circumstance. But I think it's worth emphasizing how important it is to first really try to optimize your simpler implementations first, because often that, for many practical problems, that's really all you need with Julia. And you'll get a better result when you go to parallelize it for having done so. Okay, so this is the end of this short course. So I hope that at least some of you have learned something from it. We remember that the course covered sort of two separate arms. One is the process of contributing to open source and participating in open source communities. So we talked about tools like Git and GitHub. We talked about test-driven or test-centric development practices that ensure your code will be robust and help you design it in an elegant way that is extensible and composable and all of the things that allow different bits of code to interoperate. And then we talked about processes of continuous integration and what's needed to write good documentation and the techniques for hosting your documentation that are all essential components to getting your software widely used by other people. We then also, the other sort of half of the course was really focused on how you leverage Julia to achieve good performance. You can use Julia because of the way it's designed to really escape the limitations of some older languages. It is important to use Julia well because you can handicap your code, and the consequences for your performance are quite severe if you do so. But there aren't that many things that you have to know in order to write good idiomatic Julia code. And so you can then use Julia in your just pragmatic experience with testing different things out to really quickly develop intuition about what makes a good algorithm. It's a more reliable ally to your intuition than languages that have their own idiosyncratic limitations. And it really helps you grow as a programmer in the opportunities to get the most out of your code. this course, because it's a short course, really only scratches the surface of many things. It's intended to be a taste of lots of things that I have found useful over my career, but it's certainly mastering them, or going beyond what I've told. There's lots more out there. So some places where you might explore further, I would highly recommend a far deeper dive into algorithms and data structures than I was able to give here today. Some of the tastes that I offered are sort of the basis of a much deeper exploration, but that exploration is a very worthwhile experience. If you want to extend your knowledge of how to write good, clean Julia code, at this point, one of the things that I think is most useful would be just start reading other people's code, right? Don't treat a package as a black box. Open it up in your editor and take a look at how it's implemented. Look at the code in Julia's base module. Much of Julia is written in Julia, and the people who've written that code are quite good at using Julia. And so you can learn a lot about it. Some things might look arcane and complicated, and there may be a good reason for it. It may not always be immediately apparent to you, but an awful lot of Julia's base module is very clear, very transparent, and really easy to understand the implementation. And I highly recommend reading the code that's in Julia itself. You can also improve your skills by actively participating in package development. If you have a package that you're using, but features that you'd like to make better, whether it's through the documentation or the features that the code offers, or just improving the test suite, right, to make it more robust. If you start contributing some of your time to extending these packages, if there's an active maintainer, and remember we talked about techniques to look how you judge that, odds are very good that you can essentially get custom tutoring from a more experienced Julia developer. You will submit code, say, hey, there's this new feature I want, and the person reviewing your code may get back to you with specific suggestions about how to make that code, bring that code up to the standard expected by that package, and you'll learn a lot about how to write good code in the process of that. So you can get custom tutoring from some truly outstanding developers for the mere price of a bit of your time, right? Not having to pay anything for it. And then there's a ton more, of course, to learn about parallel computing. This is really just the briefest of all mentions, and there are many excellent resources for learning about that. So with that, I wish you the very best in your Julia adventures, and thank you for